Today we'll be learning about a unique element that many people have not seen in their elemental state. This element is sodium. First of all, let's talk about the history of sodium. In the late 1700s, the voltaic pile was invented, essentially becoming one of the first efficient batteries ever used. This led to many forms of early experiments involving electrolysis. In 1807, Sir Humphrey Davy, most likely buzzed off of nitrous oxide, decided to electrolyze molten caustic soda, which is nowadays known as sodium hydroxide. He noticed the metal float up to the top and instantly combust. Little did he know that by doing this, he would discover his second element. This process later became perfected and is now known as the Castner process, named after this dude. In my crappy demonstration, I used a sardine can as a crucible for melting the sodium hydroxide, commonly sold as drain cleaner. This works better than a porcelain crucible because it conducts heat better. As I dip the cathode in, you can immediately see the anode fizz and the cathode form metal beads. Although the process may seem simple, it can be difficult to scale up, as the hydroxide ion forms water and oxygen, reacting with sodium once again. This can be very dangerous because sodium is a powerful reducing agent. When I cut a large piece of sodium, it immediately oxidizes due to the moisture and oxygen in the air. When I add it to water, the reaction becomes way more violent, as it liberates hydrogen and forms sodium hydroxide. The remaining water became alkaline, hence given group 1 the name alkali metals. I feel that there's no way to demonstrate the reactivity of this strong reducing agent other than reacting it with a strong oxidizer. I decided to use something even more oxidizing than oxygen, and that is chlorine. In a boiling flask, I add in approximately 10 grams of calcium hypochlorite and react it with equal amounts of hydrochloric acid. This forms chlorine gas, just enough to fill up the volume of my flask under STP. As I lower the heated sample of sodium into the atmosphere, you can see it, well, alright, anyways. This time I heated it up till it was burning, giving it more activation energy. And now you can see it react. This produces a very bright flame and releases lattice energy, forming salt. Salt is a crucial ingredient in our body. It's necessary for maintaining homeostasis. Things such as blood pH, nerve and muscle impulse, and cell osmosis are all reliant on the sodium cation. Now, you may wonder if there's any way to harness this bright yellow glow that sodium produces. And in fact, you would be right. Elemental sodium is often used in streetlights, and its vapor is excited with electricity, producing its distinct emission spectrum. What once powered these lights has had its own unique history in Los Angeles. In 1958, a small nuclear reactor was constructed in the Santa Susana Mountains. Chemists needed a coolant for the reactor, and unlike other metals, sodium was abundant, relatively unreactive compared to other alkali metals, and had a low enough of a melting point to qualify. The reactor actually worked quite well and powered the greater Los Angeles area, before it succumbed to a nuclear meltdown. This, along with poor management of hazardous waste, led to most of the valley being irradiated. Speaking about radiation, radioactive isotopes of sodium ions are commonly given to patients as a tracer. This radiation can easily be tracked throughout the body, uncovering any anomalies before it quickly decays. Anyways, I've bugged you enough with my lecture, and here's a scaled up reaction between sodium and water.
Back up, back up.
This is gonna work for sure.
Back up.
Okay.